maths in it, so it'll be good for us to get ready. Lesson 21, I got the power. We will learn about electric power creation and the calculations that go along with electric power. So where are we coming from to get to this point? We've just done a couple of lessons on non-ohmic resistors, which included stuff like diodes, and these are non-ohmic resistors. An ohmic resistor has a straight line, whereas a non-ohmic resistor does not necessarily have a straight line. We'd spent some time plotting those kind of resistors and sort of like exploring what they look like so that we can get an idea of, I guess, a little bit of an idea of how to sketch an exponential, which is kind of useful. Then we talked about diodes and why diodes are great. We said they're one-way paths. You know, electricity can only go one way. And then we talked about other components. We talked about capacitors. They're like charge. You can build up charge in a capacitor and let it all out at once. Talked about resistors, which are really good at both variable resistors and light-depending resistors, or photoresistors, which are ways we can detect light and as well as temperature. And then now we're moving on to this next topic. So the idea is in this topic, I want to talk about what power means. Power, and I guess this idea of how this links to this idea of energy. I guess the reason I want to talk about power is we've been talking about electronics and electricity. And normally when you talk about those things, the word power comes up a fair bit. Like we usually refer to things as, what's our power bill? So what does it mean when we say, what is power? And I also want to explore how we calculate power. But before I talk about power, I want to talk a little bit about something that I usually get skipped over. I want to talk about generating electricity. No pencil here, so there's no need for you to take notes on this section here. Just want you to listen and sort of absorb it. The universe hates charge imbalance. So that's why electrons always want to balance out the charge. That means if I've got a negative charge over here and a positive charge over here, they will move to try to balance each other out. Because now, overall, the charge is 0. When I've got a negative charge and a negative charge, they want to get away from each other. So they will repel each other. And then that will lessen the overall charge. So lower overall charge. You guys might remember this as just the idea is positives and negatives attract. Negatives, so unlike attract. I can't write, I can't spell. Unlike attract. Like repel. So when you've got two charges the same, they repel each other. So what we want to do is if we want to make these electrons move around a circuit for us, what we really want to do is we want to create a charge imbalance. We want to make those electrons, we want to create a charge imbalance because then that's going to force electrons to go from one place to another place. And this, so we will want to, and we can take advantage of these electrons as they're moving from one place to another place. I always sort of felt bad for this, kind of made me always feel bad for the electrons, even though electrons don't really have a brain or a soul or anything. But the idea is if you've got an electron and it really wants to get to this positive wall, well, we could make it jump over a couple of hurdles, make it go through some, Flappy Bird style thing, because the idea is electrons will do that. They will work hard for you if it means they get to go to a positive charge. And that's what a circuit is. It's taking advantage of the fact that electrons really want to get to the positive side of a battery or positive side of anything. So, and this is the idea of true definition of voltage. The reason that these electrons want to get to this positive charge is because they've got voltage, they've got energy. That energy is what's pulling them to that positive charge, and that's what voltage is. So how can we create a charge imbalance? What are some of the methods we can use to do that, to create a charge imbalance that we can then use to make electricity? Well, one of the easiest ways is to move the electrons with force. So if you take a piece of wool and a balloon and you rub the two together, the balloon, what will happen is the piece of material will lose a lot of its electrons. The electrons will leave the piece of material and go onto the balloon. Okay, kind of like they get brushed off. So the electrons kind of get brushed off onto the balloon. And as the electrons get brushed off onto the balloon gains a negative charge. It builds up more and more electrons. And the piece of material, that'll lose electrons, so it gains a positive charge. You look on this example here, we've got three positives and three negatives, whereas here we've got two positives and one negative. There is more positive charge. So we would say for this example here, we have created a charge imbalance, and then we can use that charge imbalance. This is the same type of charge imbalance that occurs when you build up static electricity. This is the same type of charge imbalance that occurs when you rub a plastic rod and you use it to move water. This is linked to static electricity. And this is, this is the very first type of electricity that we built up. And it was a way that we could create an electric charge, power to move something. But of course, this is great, but it can only exist for a small amount of time. Once that zap happens, where there's a static shock, or once the balloon touches the ground, all that static electricity will be gone. So what's a different way we can that we can go about doing these things? Well, another way is to move electrons with magnets. Now, I'm not going to go into, this is year 12 physics. I'm not going to go into, I'm definitely not going to go into the complex nature of how this system works. But I will talk about the basics, which is just that if you have two magnets, what those magnets will do is they will pull, magnets have a tendency to pull electrons. Now you can do that because as electrons move, they have a bit of a magnetic field. If you have enough electrons moving through a wire, then you'll actually get a magnetic field. So that means that if you have a magnetic field, you can sort of pull electrons around. The idea is that if you change that magnetic field, then you can really start pushing those electrons. So what they do is you take two big magnets and then you take a coil. And the important part of this coil is the coil can rotate. And as that coil spins around, the electrons in that coil will go flying through the coil, and that will make a charge. That will make a voltage. That will make electricity because those electrons are moving. This is how we generate electricity. All you do is so the idea is all we need is a moving coil. So if you've ever wondered, okay, well, how do we make electricity? If you take a wind farm, what a wind farm does is it's got these turning blades. In the inside of that, you've got yourself a generator. So you've got a generator is inside here. And that generator is like this. It's got a battery and it's got a moving coil. we can do the same thing in a power plant. In a power plant, what we have is we have again another turbine, so a spinning thing which is attached to a coil of wire. The only difference is that spinning thing is instead has steam coming up from it. So the reason that it turns is because this high pressure steam pushes the water. How do you get high pressure steam? You burn coal. And that high pressure steam turns this coil, which makes a current. You can also get the same sort of idea happening in water. Like if you have a waterfall, all you need to do is put some paddles in there. And then as that turns, it turns a coil and you get electricity. So the idea is, and the reason I do talk about this and so much time, spending so much time talking about this, is that pretty much from year 7 to 10, you guys get taught a lot about, oh, this is how we've got electricity. This is what electricity is. You have this idea of, oh, here is electricity. Great, cool. And then you've got this idea of, like, here is a power plant. But I don't think many times is there a link. It's like, well, how do you get electricity? We all know that coal is important for generating electricity. But the people then say, well, how do you do it? Do you attach wires up to a piece of coal? No, the idea is by burning the coal and moving this wire through a magnetic field, those electrons get, shuffled along. And the faster you move it, the more they get shuffled. And eventually that shuffling electrons will create a current. And that is how that's a way that we can generate electricity for thousands of homes. Great, cool, but that doesn't help me when I'm sitting in the middle of the outback. There's got to be another way we can generate electricity, and there is. You can generate electricity with chemistry as well. Remember, electricity is just moving charge. That charge that's moving doesn't have to be electrons. You can actually let's take sodium and fluorine, right? Now you guys probably remember from term 1, hopefully you remember, that sodium has 1 electron and fluorine has 7. This is the Lewis dot 7 in its outer shell, okay? The reason that they pair together is because of the classic, if this guy loses an electron, then this will have a full shell of 8. This will have a full shell of 8 because underneath it's got 8 electrons. So it wants to lose an electron. It's happy to lose an electron. It's happy to gain an electron. This is called ionic bonding because it's stealing. So this electron really wants to get over here. Well, that electron really wants to get over there. Let's make it work for it. How can we make it work for it? By splitting them apart. This electron still really wants to get to over here to have a full shell. There is still an interest for that electron to get there. So if I, give it a piece of wire, well, then that electron will jump down the wire to get to the fluorine. Okay, that's pretty much all the battery is that you are creating a path. This is now the wire that you would attach. This would become this would be the negative part of the battery. And this is the positive part because this is where the electrons want to get to. This is where the electrons want to get away from. So this is our wire. The only other thing that we need in a battery, and this is now getting a bit advanced, is you need to have, even though it's called the negative part of the battery, once it loses its electron, that sodium is going to be positive. The only thing we need to talk about a little bit extra is this. If I build up lots and lots of positive sodium atoms, that's going to make this so positive, then the electrons aren't going to want to move. The electrons are going to go, whoa, 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 and they're going to stop, and they're going to go, wait a second. It's more positive this way than it is this way. So if they're going to change their mind, and then you're going to have no current. So to make sure that you deal with that, you also need to have a bit of a salt solution here. And the salt solution has a bunch of cations and anions, and they swap places. As this builds up positive charge, you bring in more anions to cancel out that positive charge. As this gets more negative charge, you bring in this positive to cancel it out. And that's pretty much what a battery is. Obviously, it's a fair bit more complex than that, but the basic idea is that you have the electrons want to go from one place to another place, and you just use a wire and then maybe you put a light bulb in it. You use a wire with a light bulb to take advantage of the fact the electrons want to move. The only other thing that's extra is you need to balance out those charges as they get created. You need to balance out this positive charge with negative charges. Now, you wouldn't actually use a sodium fluorine battery. Okay, that doesn't actually exist. It's not a thing that exists. But you can have a lithium ion battery. So a lithium, being metal, is very, very similar to sodium. It wants to lose its electrons. So lithium is a really good thing. And that's what a lot of mobile phones, a lot of laptops have in them. And yeah, it's the same sort of idea that lithium wants to get rid of its electrons. It'll push its electrons through a circuit to get to something that can accept electrons, like fluorine or chlorine or something similar to that. The chemistry is a little bit more complicated in real life, but I'm just trying to dumb it down, make it simple. Just say sodium hates electrons, wants to get rid of them. Fluorine loves electrons, so you guys can clearly see why the electrons are moving. Now, in all honesty, those 3 slides that I went through, I just wanted to give you guys some context. I don't really expect you guys to memorize this stuff. There is no pencil on this slide. This is just sort of background information. I think it's important background information because it's really important this slide here might provide you with some really good insight. If you choose to do year 11 chemistry, maybe you start to understand, that's how batteries work. Batteries force the electrons to go through a wire so we can take advantage of it. Maybe if you do physics, you can be like, oh, that's how we generate electricity, by, having a coil move through a magnet. Maybe just in general, you're like, I never knew how moving water could possibly make electricity. But the main ideas that I do want you to walk away with, and the slide that I do want you to copy down, is this one at the very end. Electricity is created by moving electrons, trying to balance out charge imbalance. And I'm going to write that down here, charge imbalance. The 3 ways that we can create a charge imbalance is by pushing electrons off a substance. That would be with a force. That's linked with static electricity. The second one is by pushing electrons around with a magnet. The third one is by pulling electrons around using chemical attraction. Now, if you're copying this down, I'll give you guys a little bit of time to copy this down. If you're just going to, maybe screenshot it or save it later and then copy it down later, then that's okay. But I will spend a bit of time talking about this for those people that are writing this down in their books. This last one, pulling electrons around using chemical attraction. By the way, if you're interested, this is where a lot of chemical reactions can be turned into batteries if you just make sure you set your circuit up properly. But another little point that I wanted to draw attention to here as well is that this is also how solar panels work. Solar panels actually, once light hits them, electrons get excited and they can move around. And then because of the chemical attraction, those electrons can then start to make a current. And that's how a solar panel works, is more like the bottom one. Whereas, stuff like nuclear power is the middle one. Nuclear power all you really use nuclear power for is just a different way to heat up water. Rather than using coal to burn it, you just use, nuclear radiation to heat up the water. You could even just pump the water straight into a massive hole, straight into a massive hole near some lava and get it really hot at the bottom of the lava, and then pipe it back up as steam, and then that's geothermal energy. So that's another way you could create steam to turn a turbine. So these are different ways we can create power. So what is power? Power is measured in watts, and it has the symbol P. It is a measure of the amount of energy, voltage supplied every second by the current. So therefore the formula is P equals VI. Now you guys might have heard the word watts before. You probably heard voltage and current before, but you may have heard watts. 60 watt light globe is what people would say, which means that a 60 watt light globe is going to take 60 volts every second, or 60 volts at 1 amp, or you can use that to figure out, well, how many volts and how many amps. We can actually create a couple of formulas with power though by doing something called substitution. I'm going to substitute V equals IR into this equation. Grab a look what happens. P equals, instead of V, I'm going to write IR times I. That actually creates a formula, I times I, P equals I squared R. This is a different formula. It's a different way of writing down the power formula. And you could even do one more by, instead of substituting V equals IR, you could substitute I equals V on R into that formula. Can anyone tell me what formula would you get if you substituted I equals V and R into that equation? You can write it in chat, or you can say it out loud. Up to you guys. Someone said something. I'm going to hope it's relevant. It is not. It is a picture of Pikachu. Okay. Can someone tell me what is, if I substitute I equals VR into this formula, here, what type of formula could I get? Or do people need help? P equals VV over R. Yeah, that's pretty much it. Thank you, Min. P equals V times V over R, which is going to turn into V squared on R. Just another formula, just in case you wanted to know. So but this is the main formula that we're going to be using a lot. P equals VI. Let's use P equals VI. Let's test it out. Okay, let's see if we can work out a formula with P equals VI. Okay, so hold on. Before I jump in there, I've got to teach you guys one more formula. Sorry, it's energy. Now, remember we talked about energy. We said voltage has an amount of energy. So, and we just talked about power. Power is actually linked to energy. Power is like the amount of energy given every second. So, energy is the amount of energy voltage supplied by the circuit in a single second. So just like how power is like voltage times current, if you wanted to say, well, how long is it for? So it has the symbol E and it's measured in joules. Okay, so energy is the power multiplied by the time. You know you've got a 60-watt device. In 1 second, it will deliver 60 joules. In 2 seconds, it'll deliver 120 joules. And so you can start to see, okay, cool. So now we know if I've got a 60-watt light globe, how much energy is it pumping out every second? That's sort of pretty much what power is how much energy is it pumping out every second. And if I multiply that by time, then I can find out how much energy. I can also use this to make this. So I can also use this to make this formula here. Energy equals the voltage times the current times the time. I'm not going to bother with this because I don't want to confuse you guys too much. I just want to give you guys these formulas. So we've actually got 3 really important formulas so far. P equals VI, E equals VIT, and E equals PT. Or you can think of it as P equals E divided by T. It doesn't matter. It doesn't really matter which way you think about it. So those are our new formulas. These should be written down somewhere because we're going to use these guys a bit. And this is going to be the bulk of motion 4. Is that what we're up to? Motion 4, which is going to be mostly about how do you manipulate these values. So let's use them. The circuit has 12 volts and is running at 150 milliamps. What power is the circuit running at? Well, let's write down our 3 formulas. P equals VI, E equals VIT, E equals P times T. And we've got other ones, but we're just going to stick to those ones. So what power is it running at? I'm going to calculate power. I've got a voltage, I've got a current. This is going to be pretty quick for me to work out. Power equals voltage times current. The voltage is 12. The current is 150 milliamps. Be careful about the milliamps part. So it's going to be 0.150. You don't know how I got that? Remember, milliamps means divide by 1,000 to turn into amps. Same way as that if you have 2 meters, you know, then that means, well, if you've got 3 millimeters, that means you've got 0.003 meters. Because remember, I just divide by 1,000. So 12 times 0.15 is 1.8 watts. Thank you, John. Now, if I want to now know, okay, well, if the circuit is on for 2 minutes, how much energy would be used? Okay. You would then think, well, I'm looking for energy. You can actually either use this one or this one. I'm going to stick to this one at the top because we know the power, so we could just substitute it in. So E equals VIT, and you go 12 times 0.150 times 2. And then you'd be wrong. Dead wrong. Because you don't multiply it by 2. You actually multiply it by 120. Good job, Jason. Nailed it. Because we're using scientific notation. So scientific not notation. Scientific integers. We're using, what's the word? Scientific units. Sorry, I'll get there eventually. I bet someone corrected me. Yeah, I know. So 2 minutes turns into 120 seconds. So that's what the one that we need to use. We can't use minutes, we have to use seconds because seconds are the scientific international registered idea. Milliamps is not, amps is. So when you times 12, when you multiply this by 120, that's going to give you 216 watts. 260, oh, joules. Joules, 216 joules. Perfect. Great. That's how we use them. We've just got these three formulas. And normally what I would now do is I'd wrap up the end of the lesson, except that I'm going to throw a bit of a spanner in the works. I'm going to talk to you guys about a different way to talk about energy. Joules are a great way to talk about energy, but there is another way. The other way to talk about energy is kWh. Now, before I talk about kWh, I'm going to tell you guys a little story. I've been teaching this subject for a couple of years now. I always find teaching kilowatt hours one thing I'm really proud of. The reason I find it really proud of is the first year that I taught it to my little year 10 students, I stuffed it up so badly. I did such a bad job of teaching kilowatt hours. So many students walked away confused. I felt so guilty. And I just was like, oh my God, I can't teach this because I just, I have no idea how to teach it properly. After the years, I've gotten better and better and better at teaching it. Until now, I'm really quite happy with how I teach this stuff. So let's go. Hopefully this makes sense to you because it's been a couple of years. You guys are lucky that you're learning it. So kilowatt hours is another unit of energy. It's like joules. There are even more units of energy other than, well, I should write down what it's called. So kilowatt hours. There are other units of energy rather than joules. You may have heard of calories. Calories are another form of joules, another form of energy. But I guess we sort of use different, because the energy is such a broad topic, we need to make sure we have different ways to calculate it in different fields. So calories, we use that a lot to do with food and like fuel. These are when we use, whereas kilowatt hours is really the electricity version of energy. You wouldn't go around and say, wow, this Big Mac has 0.1 kilowatt hours worth of energy. People go, what the heck is wrong with you? Same way you wouldn't say, wow, we've used 3,000 calories of energy on lighting this week. And you're like, what? No, that doesn't make sense. You would use the type of energy that sort of is attributed to the field that you're talking about. That's not to say that it is not possible for you guys to convert the amount of energy used to charge up a light bulb in amount of Big Mac hamburgers, which I have done once. I think it's like the amount of energy your house needs, a fridge needs to run is equivalent to one Big Mac's worth of energy. And it's a bit weird, but I did the maths, but yeah. So kilowatt hours comes from the equation E equals PT. Now you might, I didn't show you this equation, but hopefully you guys can figure out, oh no, I did. I just called it E equals P times T, so it's just E equals PT. So what we do, is we use kilowatts for power and hours for time. These are not the standard units. You would normally just use watts and seconds. You would not use kilowatts and hours. They are not the standard units. So we're actually sort of breaking the rules just a little bit. And that's okay. Like, we can do that because we can make our own units. You can make your own units for anything, but these are our own units. So a 1 kilowatt hour is the amount of energy a 1 kilowatt device would use in an hour. And that's sort of, okay, so what's a 1 kilowatt device? Well, an example of a 1 kilowatt device might be I think it's like, a good one would be a hairdryer. A hairdryer is a 1 kilowatt device. If you kept on a hairdryer for a full hour, that's what 1 kilowatt hour worth of energy is. Okay? Now, if you have something like a fridge, which is 0.1 kilowatts, in order to get a kilowatt hour, you would have to keep that fridge on for 10 hours. So you'd have to keep a fridge on for 10 hours to emit the same amount of energy as a hairdryer does in one. And hopefully that makes sense to you, because you're like, well, fridge must be low power, which it is. And whereas a hairdryer has got a lot of power, it's high power. So it's just a different way to talk about it. And why do we use them? Really quickly, why do we use kilowatt hours? If we've got joules already, then why do we use kilowatt hours? Because of that reason. It's so easy to be able to say, oh, you know, a fridge, that's 100, that's going to make about 2 kilowatt hours in a day. About 1 kilowatt hour in a day. You can go, or 2 kilowatt hours in a day. You can go, a hairdryer, that's going to use 1 kilowatt hour if you leave it on for an hour. You can, rather than saying, oh, a fridge is going to use 3,600 joules or something, it's just ones and twos. That's why we do it. It makes calculations a fair bit easier. And they actually put this on electrical bills that you take home, because it's just a bit easier. So 1 kilowatt, just in case you wanted to know, there is a way to convert from kilowatt hours to joules. 1 kilowatt is equal to 1,000 watts, which is 1,000 joules per second. That means that 1 hour is 60 minutes times 60 seconds is 3,600 seconds. So 1 kilowatt hour is 1,000 joules per second for 3,600 seconds, or 3.6 million joules. So 1 kilowatt hour equals 3.6 million joules. If you ever want to be like, you can convert from one of them to the other one quite easily. But I actually never tell students to convert. Never. I go, what do you mean? Why don't you tell students to convert? It's like, you know, the same way you could convert meters to centimeters. It's like, no, I don't teach you guys how to convert. I think the smartest way to do these problems is to do the problem twice. Let me show you how. An Xbox uses 200 watts when in use. If it runs for 2.5 hours, how much energy does it deliver in joules and in kilowatt hours? Well, let's figure this out. Let's start first in joules. In joules, we would go E equals PT. We've got 200 watts times, and this time is 2.5 hours. But again, we're not going to use 2.5 hours. We're going to go 2.5 times 60 to find out how many minutes. We're going to multiply by 60 again to find out how many seconds. So 200, I'm going to put this in my calculator now, 200 times 2.5 times 60 times 60. That comes out to be, there's 1, 2, 3, 4, 1, 8, 1, 2, 1, 2, 3. So 1.8 million joules. Now, I could convert that into, I could convert this into kilowatt hours, but instead, I recommend for you guys just to do the kilowatt hour calculation again. The reason that I think it's better to do it again is because you don't have to muck around with conversions. How do you do it? Kilowatt hours? Okay, energy equals power times time. This time though, the power, I can't give it as watts. I have to convert 200 watts to 0.2 kilowatts. So I have 0.2 kilowatts times 2.5 because it's 2.5 hours. 0.2 times 2.5 gives us 0.5 kilowatt hours. And I think that's a little bit, yeah, that sort of is a little bit easier. That means that even after using an Xbox for, even after using an Xbox for 2.5 hours, you've only used 0.5 kilowatt hours. However, I haven't mentioned how much energy the TV is going to use while you're using it for that 2.5 hours. But we'll just ignore that for the meantime. Now, which of these is easier for a person who's at home, who isn't a physicist, who isn't an engineer, to work out how much energy they're using? They're going to prefer kilowatt hours. 0.5 kilowatt hours, that makes sense. I can add 0.5 and 0.5. If he uses an Xbox for 5 hours, that's going to be 1 kilowatt hour. But dealing with big, crazy, ugly numbers like 1.8 million joules, yeah, nah, it's not going to work. Okay, your turn. I want you guys, you know what? I'm not going to do this for you. I want you guys to calculate this on your own. Okay? I'm going to give you guys, what am I going to give you guys? I'm going to set a timer. I'm going to give you guys 2 minutes. I'm going to give you guys 2 minutes to calculate this. Calculate this on your own, and then we'll go through the answers together. So give it a try. Use the technique. If you want to know how to use the technique, the answers are directly right above you. Work it out, put it in chat, and we'll compare the answers. Wow, did you actually calculate that, John? If so, I am impressed. I think you got your calculation a little bit wrong, John. So a Big Mac is about 2.3 million. So you're looking at about, oh no, you're right, 2.3 million, 1.8 divided by 1,000 divided by 2,300. Yeah, you're right, 80% of a Big Mac. So you could actually take a bite out of it and then shove it into your Xbox and play it for 2.5 hours. I don't think that's physically possible though. No, I don't want the answer to the one on the bottom in Big Mac's worth of energy. I want the answer in terms of kilowatt hours. So guys, Jason's got an answer. Good. I don't know. It could be wrong. We'll find out. Don't worry. All right. There we go. Let's calculate it. Got one answer from Jason. No one else offered an answer. Oh no. No, John calculated it, but calculated it in Big Mac's worth of energy, which is not Big Mac's. I guess that's the thing. Now you guys have 3 units of energy: joules, kilowatt hours, and Big Mac's. Like, oh man, how many? But I'm not going to ask you on an exam or a test how many Big Mac's worth of energy goes into this house or this, whatever. I'm not saying you can't do it though. It's more of a shoot. Can you? It's could you? Listen, John, if you do that, I don't know. If you get the answer completely correct and then you convert it to Big Macs, then I'll give you the marks. Anyway, let's move on. So start off with, we'll start off with dark blue, we'll do joules. So E equals PT. We've got here 800 watts, and this time is 3 minutes. 3 minutes turns into 180 seconds.
Hey, Mister, what does E equal again?
Energy.
Energy. Yeah, I knew that. Thank you.
That's right. 800 times 180 gives you 144,000 joules. Okay, so what about kilowatt hours? Again, I would straight away jump into just doing the equation again, rather than trying to divide and multiply this by 3.6 million. E equals PT. In this case, the power, we know we don't use 800 watts, we use 0.8 kilowatts. We don't use 3 minutes because 3 minutes needs to be converted into 3 divided by 60 equals 0.05 hours times 3 divided by 60 gives you 0.04 roughly. Yeah, 0.04 kilowatt hours. Let's see if that's what Jason said, because I'm actually going to just base whether or not I got the answer right. Yeah, okay. Aaron said that, and yeah. Yep, that's what I got. Beautiful. And then because you know, why not? 144,000 divided by what was it? 23 million divided by 2. So this here is not necessary, but just because I can. .062 Big Macs. Okay. Now, yeah. Okay. So we can convert things to Big Macs worth of energy. You probably shouldn't, but you can. Last example, I think, for today. I think this is the last example for today. Let me just check. Oh, no, second last, but the last one's really easy. A fridge uses 3.6 kilowatt hours in a full day, 24 hours. What is the power rating of the fridge? So this is just the idea of E equals PT. But now we want to know what P is. So if I change this to E over T equals P, how did I do that? I divided both sides by T. If I divide both sides by T, that makes P the subject. Now, if I happen to know that the energy was 3.6 kilowatt hours divided by 24, because that's how many hours are in a day, 3.6 divided by 24, 0.15 kilowatts. That's the energy of the fridge, which means that the fridge has has a power rating of 150 watts. And I'm pretty happy with that. So it's just, you can be asked to manipulate these kinds of formulas. That's not too difficult to do. You could be asked, but yeah, you have to be careful because I manipulated it, my answer is a power answer, but because it comes from kilowatt hours, my answer will be in kilowatts. If you wanted to find out the time, you divide it by power, your answer would be in hours. That's one of the things you've got to be careful about whenever you use units in an equation. If you're using meters and seconds, your answers will come out as meters and seconds. If you're using kilometers and hours, your answers come out as kilometers and hours. The units stay the same. You just got to be careful. The very last thing, because I want to get through this, because then we can finish just a smidgen early, is efficiency. Now, efficiency in percentage is linked to power, is linked to this whole thing, but I wanted to talk about it. So if you've got like let's just say you've got a light bulb, and your light bulb is emitting like light's coming out of your light bulb. But what it's also going to do is it's also going to heat up. Now, the useful energy is going to be for a light bulb is going to be light, but the total energy is going to be everything. It's going to be the light, it's going to be the heat. If you've got a motor, it's going to be the useful energy will be the movement, but the unuseful energy will be the heat, will be the sound, any energy you don't want. So when we talk about efficiency, we usually talk about, well, how much useful energy is coming out versus what's the total amount of energy that's being used. So let's grab a quick look at an example down the bottom here. When a lump of coal is burned, it releases 12,000 joules worth of energy. Okay. That's probably important, so I'm going to underline that. It is converted into 3,400 joules of electricity. What is the efficiency of this process? Okay, so the efficiency, well, the question becomes, which one of these is the useful energy? The energy released or the energy converted to electricity? Which one's the use? Can someone tell me which one's useful? The 3,400 or the 12,000? The 3,400 is the useful energy. So efficiency is equal to useful divided by total. And I'm just running E because I can't be bothered writing energy. So the useful energy is 3,400 joules. Total energy is 12,000. And we're going to multiply this by 100 at the end. 3,400 divided by 12,000 gives you the nice little round number of 28%. 28%. So that's the efficiency. 28% of the coal is being converted into useful energy. Yeah, you could say 28 and a third, but I'm just going to stick to 28% because I'm lazy and round it down. Now, this could be used for coal into electricity. It could be used for a sound system. You put in 10 volts, you put in 10 joules or 10 kilowatt hours of energy into a speaker, but you only get 6 kilowatt hours worth of energy out. What's the efficiency? Efficiency is just really tied into these sort of things because nothing that converts energy is ever 100% efficient. You will never get 100% efficiency, and hopefully you guys can see you can never get more than 100% efficiency. You can't get more energy out of something than the total amount of energy. So it's impossible to get more than 100%. So yeah, 72% gets wasted. It's not very efficient. That's why, ladies and gents, we are desperately trying to move away from coal because not only is it completely destroying the earth because it's got more greenhouse gas, it's also really, really not efficient. If you compare this to something like, I don't know, like electrolytic cells, they're really, really efficient. Though saying that the solar panels are really poorly efficient, solar panels are 10% efficient usually. That's the best solar panels that we have, which means that they get, if you get 100 joules from the sun, only 10 of it is turned into electricity. You might think, well, that's crap. But remember, one, solar panels, they're not adding carbon dioxide into the atmosphere. And two, they can run like, all through the day. There are some disadvantages with solar. Let's not kid ourselves. You can't run a solar panel at night. It just doesn't work. So, what does that say? But I think that we should definitely be moving to more renewable energy sources because, in my opinion, we've got to get away from coal, even if it's just for the fact that it's a non-renewable energy source. Even if it wasn't destroying the atmosphere and causing global warming, there's only so much coal. Eventually we're going to run out, and what do we do when that happens? I got no answers here. All right, guys. Yeah, let's just stop it here, ladies and gents. That's the end of the lesson. I'm going to let you guys go a little bit early. Don't tell Miss Panasiris. What we're going to be doing tomorrow is we're going to be talking a little bit more about energy and how it gets used, and we're probably going to start working on electronics 4 because I think that'll be pretty quick to do now that you guys know this, and you guys can ask me some questions. Anyway, that's all. Thank you for listening, and I will chat to you guys tomorrow.